I'm going to have the same going in as the same going out? Let's see. You have your own guess. So what happened? They got longer. It's because the vectors over here are getting longer, right? But they're still canceling each other out, aren't they? Because the ones that are coming in are as big as the ones going out. So we're still getting the same divergence here. You can add more vectors if you want to see more vectors in action here. Take them away. You can zoom in if you want to take a closer look at them. And you can zoom way in. I'm just looking, I haven't looked at this in a long time to see what the hell I put together here. Okay, so this is a pretty uninteresting vector field, isn't it? In terms of divergence, it's pretty boring. The divergence is 0. It looks like everywhere, right? If I move this up, anything going to happen? No. Move it to the left. Div is always staying the same, right? All right, so let's change to a different vector field. And let's go to the initial settings here. All right, more interesting. How about that one? Do you think we're going to get some interesting things? Yes. Let's see. Boom, right here at the origin. Oh, crap. Div is 0 still. Let me see, zoom into that. Div is 0. Let me show some more vectors. No? Okay, well, let's move it. Up or down? Left or right? Left? Ah, there we go. Okay, so see, we got more red coming in. Like the number of vectors going in might be equal to the number of vectors going out, but it's the length of the vectors that's overpowering what's going out. So if there's more force going in, the force coming out is not as much. So it's almost like pressure, you could say. More pressure on this side than on that side. Make sense? What about if I move it up? Oh yeah, notice the answer is negative. The answer is negative because there's more going in than coming out. Moving it up. Oh boy, we've got a lot of very long red vectors going into that, overwhelming the green coming out. You see it? Probably going to have to move to the other side. I don't know. Can I get my div to be positive? Let's see. Here we go. Oh, over here I've got some positive div. There we go. Let me zoom back out. I moved too far. I think you can kind of see it here. More going out. The green ones are longer. That's kind of cool, huh? All right. What is this in three-dimensional space? Instead of on a flat piece of paper and a point and a little circle, it's going to be three-dimensional space, a point, and a sphere, a little ball around it. Well, I took the time to go ahead and put that together a couple of years ago. Here it is. So remember, this is a point, right? This is a point. But I'm making this little ball around it, and I'm looking around all the ball, and I'm trying to figure out if I've got more going in than I do have coming out. And I'm not showing you the vector field here. Yeah, I can't show you the vector field. You just have to believe me that there's a vector field here, all right? So here it is. Oh, shit, our div's big, right? Got a lot of vectors coming out of this ball, and they're really long compared to the ones going in. Zoom in on this ball. Let's get more vectors in there. Right, you see them, all these little ones in here being overpowered by all the big ones coming out. What is that?
Looks like an asteroid.
An asteroid? Yeah. So like here we are, right? There's us right here. Yes. And we're probably thinking to ourselves, right? What are we thinking at this moment, right before impact? Positive div. Positive div. Boom! It's over. All right. Let's move this thing around. Maybe we can get some negative div here. Oh, here we go. Something's happening over here in the field. Now we're getting negative div.
We're dodging.
Yeah. I think you get the idea. Yes? So in terms of, curl gave us our tendency of our fluid to want to twist, right? To turn, to curl. The div measures the tendency of the fluid to diverge or leave a point. So it's like, it's kind of difficult to explain. I know some of you have heard of divergence before. Do you have any other good? No? No? Okay, divergence, tendency of the fluid to diverge or leave a point. So if you're at the point, if you've got positive divergence, there's more of a tendency for things to flow away from it than there are to flow into it, right? So if you're at a point and you move a little bit off the point, most likely you're going to be moving away faster than you are going to be moving back towards it. So anytime we have this, we go to a point. If the div is positive, then we call that point a source point, because things are wanting to move away. So it's like you're at a campfire, you can feel the heat coming off it. It's a heat source, things are coming out of it. So when your div is positive, things are coming out of the point, it's a source. If your div is negative, then things are wanting to go in, that's called a sink. And anytime your div is 0, it's called incompressible. And the idea is, that it, like a solid block, nothing wants to go in, nothing wants to go out. There's equal going in than there is going out, so it's just kind of static, right? Incompressible. Now, the computation of div is much easier than the computation of curl. So easy, in fact, that I can just do one example and we can move on. So div, the notation for it is this, div f. It does involve del again. There's del. That's a differential operator. But instead of crossing it with f, we dot it. And we like dotting vectors, right? Dotting vectors is so much easier to do. So if I take, I don't think I have it written here, but this is del. Right? That's del. And this is f. P, Q, R. Then if I dot them, I do this and this together, right? Which means the partial of P with respect to x, because it's a dot product, plus partial of Q with respect to y, plus partial of R with respect to z. So it's super easy. All you're doing is taking the derivative of each of these component functions with respect to x, y, and z respectively, and adding them together. And that's it. Your answer is a scalar. That's the problem we had earlier, where we were asked to find the curl and the magnitude of the curl. Remember that one? That took us a little bit. Let's do div. Div f is del dot f, which is, I'm just going to do this without writing the formula. It's the partial of this with respect to x. 2x, y, z. Vector? No, plus partial of this with respect to y. 2x, y, z, plus partial of this with respect to z. 2x, y, z, which is 6x, y, z. That's your div. So the div of this particular vector field depends on where you are, right? Your x, y, and z coordinates all contribute to whether or not you're going to have div or not. Now, at the point 2, 1, 0, what's your div? 0, because the z is 0. We happy? Now, this is going to look weird. But remember Green's theorem, right? Remember Green's theorem? Yes? Green's theorem says that the line integral along closed curve C, P dx plus Q dy is equal to double integral over the region D that C encloses of partial Q with respect to x minus partial p with respect to y dA, right? That's Green's theorem. But this, oh, and this right here, sorry, this is equal to line integral over c of f dot dr. Do you agree with that? This is this, yes. Which is this. So look at this new formula for Green's theorem. If this is equal to this, right? That's equal to this. That means that this right here, oops, I thought I silenced that, must be equal to this right here. Do you agree with that or not? Yeah, what's the curl of f? Well, let's go back in the notes real quick. Curl of f. Where are you? There it is. Okay, there's the curl of f, right? If I dot that with k, because that's what that formula said just a second ago, dot that with k, what's the k vector? IJK? 0, 0, 1, right? If I dot these, the 0 kills off the first one, the 0 kills off the second one, and 1 times this is that, right? It's another way of writing Green's theorem with all vectors in it instead of having this right here. These are scalar functions, right? So that's why we call that a vector version of Green's theorem. Okay, understand? That will come into play later. And the next one, for sure, is going to come into play later. It's another way of writing Green's theorem. All right? And for now, what I want you to do is just remember this is here. I'll refer back to it later. I don't want to derive this. The book does it. They do a decent job. I want to spend some time. I would want to spend probably 20 minutes to 30 minutes deriving that and making sure you understand where it comes from. I'm not going to take the time. Just later on when I refer back to this, right, have a little note somewhere that says, you've got the formula sheets, right? Yeah. You've got this in there, all right? Now, there are a bunch of identities with curl and div. And I have one here that I'm not going to work through. I just want to show you like the basic idea behind it. If you take the div of the cross product of two vectors, it's equal to g dot curl of f minus f dot curl of g. And this is an identity. And do you remember in pre-cal when you had to show an identity, like you started with one side and turned it into the other side? That's what you would do with this. And this is in your notes. You can follow this. They started with the left side, and they turned this into the right side. All right? I think what I'll do is you almost had one of those on your take-home, but I took it off. It was the last problem. I took it off. I might offer that as an extra credit, or maybe something to that effect on the final as an extra credit, without ever showing you how this is done. See if someone would want to tackle that. Now, your homework assignment has a few of these. I think there's 2 of these, which I did not put solutions up for. Again, those, just realize those are going to be bonus problems, so you don't have to do those. There's the homework. I'm talking about 21 and 23 are identities. All right. That's it. We doing all right? 3-5? It's pretty straightforward, 3-5, right? It's just computations.
So just 6, 7, and 8 more?
Pardon?
13, 6, 7, and 8, that's it?
13, 6. Oh, yes. No, there's a section 9, I believe. Maybe not. Yeah, there's 9. But section 9 is only 3 or 4 pages long. All right, we are going to start 3.6, but not heavily. I'm just going to get you going with this, and then I'm going to have a handout. We're going to start talking through this handout. Okay, remember, way back from chapter 10, look, this is a really important section, all right? I lose a lot of students right here in this section. So ask me questions. When I hand you this handout in a little while, if you have questions, let's resolve those, because if you can't do what's in this section, the next 3 sections are going to be impossible, because you have to be able to do what this section asks you to do. All right, remember from chapter 10 that if we defined a vector function r of t to be f of t, g of t, or if we do it 3-dimensionally, then this drew a curve. And I told you back then that later on we would be able to do something like this and be able to draw surfaces. And that's what this section is about. Can we draw a surface with a vector function? And the answer is yes. Okay? If we have a vector function, and this time, instead of having one variable that we're plugging in, t, we plug in 2 variables, which we call u and v. I'm going to write this over here because it's going to be so important to us. If we have 2 variables being plugged in, and then a 3-dimensional vector, okay, where the x somehow depends on u and v, the y somehow depends on u and v, and the z somehow depends on u and v, then if you define it that way, and you let you put some restrictions on u and v, give them some domain restrictions, then you will draw a surface in 3-dimensional space. The book does not take a lot of effort and time in letting you practice converting a surface into that form. So that's what I would like to do now. I'd like to hand you this worksheet, and we are going to go through, and there's, I think, examples A through F, and we're going to come up with these parametric functions. It's called parametric surfaces. Go ahead and hand those all the way back. You know what? Let me get you 2 more. Whoa. If you could hand those back, please. 4, 5. There you go. These are hard to see from the drawings. I don't believe that this is up. Someone can tell me, is there a CDF file on the website that has this? It's hard to see with what you have in your hands, so no, you can tell me later. Okay, you ready? I want us to come up with a parametric surface. In other words, a function